Hello everyone. Today we are going to learn a little bit more about 3D vectors, including how to find the different angles that we have for those vectors. And finally, we'll wrap up with some interesting properties for those vectors. All right, so to start off, last week we started to learn the basics of 3D vectors, and we saw that 3D vectors can be represented with 3 axes. So I'm gonna add those axes in really quick with a vector. All right, so we're going to start off with 3 axes, x, y, and z. I've only drawn the positive parts of these axes for now. And then some vector v, which lies in this space, the positive direction for all 3 of these. So v is kind of coming towards us in a way. We can describe v in terms of its magnitude and also the 3 different angles that it forms between the x, y, and z axes. I'm going to start off with the x-axis. So imagine for a second here that we're drawing the triangle formed between the x-axis and our angle v. This one's kind of skinny from this angle. And this triangle is flat. We can think about it as a flat triangle between x and v. And we can, if we look down directly on this triangle, we can write it out in 2 dimensions, and it would look like this. So we have v coming from the origin. We have x in this direction. So I'm kind of rotating it too. And then we're looking at the triangle formed here. And I drew this triangle so that the side here is at a right angle to the x-axis. So that way we have a right triangle. This angle in between the vector and the positive x-axis we could call alpha. So this angle right here is alpha. So this is one of the angles we can use to describe v. In order to find this angle, so by drawing this triangle, we can find this angle using right triangle trigonometry. Here we can see that the cosine of alpha is equal to, and cosine is adjacent over hypotenuse. So let's just call this h, or we could more specifically say the magnitude of v. So over hypotenuse, magnitude of v. And then the adjacent side is going to be how far in the x direction this vector spans, how far in the x direction this vector is moving. And what we can do is consider v as a vector split up and written out with components. So v equals ai plus bj plus ck. So a is the x direction component, b is the y direction component, and c is the z direction component. So here, the x component is going to be a, so that adjacent side. So the cosine of alpha is a over the magnitude of v. We can also consider triangles drawn between the vector and the other axes as well. So let's take a look at the y-axis. So this one here, we can draw a triangle here, for example. Oops, sorry. And this should be going to the end of the arrow too. So it should be about right here. And this triangle, it looks flat, but it's actually kind of coming towards us. The hypotenuse, the vector is closer to us, so it's kind of at an angle. If we were to draw this out, we would have the vector v here. We have the y-axis here. Our angle we're looking at here, we could call this angle beta. And we drew a line perpendicular to the y-axis, all the way up to the end of the vector. So we're looking at beta, which is this angle here, beta. And to find beta, we can use right triangle trigonometry again. Cosine of beta is equal to, and again, this is the y component, so b, and this vector here is v, so the hypotenuse is the magnitude of v, b over magnitude of v. So we looked at the x-axis, the y-axis. Finally, our last angle to examine is relative to the z-axis. So what we can do is, again, draw a triangle from the z-axis to the vector. So add in a line there. That's a right angle to the z-axis. And again, this triangle, this point, for example, is closer to us than the z-axis is. And we can draw this out as over here. I'll go ahead and add the z-axis. Actually, let's just keep it vertical. Z-axis. Here we have our vector b. And then we drew, or we added it in this line here, perpendicular to the z-axis. So this is the triangle formed between the z-axis and our vector v. And again, to find our angle, and let's call this angle gamma. So gamma kind of looks like this, or I'll be drawing it like this. And to find this, we can look at the z component. So this is the z component, which is c. And we can look at the magnitude of our vector v. So cosine of gamma is equal to c over magnitude of v. So we can use the components. So for example, if we're given the equation of our vector, the components x, y, and z, we can use those components to find these angles and then describe our vector using 3 angles and its magnitude in space. And for these equations to the right, we can write these out and be a little bit more clear how they're related to a, b, and c by thinking about how we define magnitude of vectors in 3D space. So just thinking about our previous video, the magnitude of a vector v in 3D space is the square root of a squared plus b squared plus c squared. So we can replace magnitude of v in all of these with that equation. And we end up with the 3 equations, which I'll write down here. We have cosine of alpha equals a over square root of a squared plus b squared plus c squared. Cosine of beta, and again, this is alpha is the x-axis, beta is between the y-axis, is b over square root of, a squared plus b squared plus c squared. And then finally, cosine of gamma is c over square root of a squared plus b squared plus c squared. So here we have the 3 different equations we can use to find the 3 angles that our vector forms between the x, y, and z axes. And if we consider all of these equations together, we come to a pretty interesting conclusion, which is, well, let's write it out, which is that cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma is equal to 1. So we have this equation here, and we can use this, for example, to quickly find, if we know 2 of the angles, we can find the 3rd angle. And this is true because if we replace cosine with the right sides that we see here, and then square it, cosine squared of alpha is going to be, well, we could square the numerator and denominator separately, so a squared over, and if we square square root, it undoes the square root, so a squared plus b squared plus c squared. For cosine beta, we get b squared over a squared plus b squared plus c squared. And then finally, for cosine gamma, we get c squared over a squared plus b squared plus c squared. And then we can see that we have a common denominator, so we can add up a squared plus b squared plus c squared in the numerator. We can add up the numerators. And lastly, notice that we have the same numerator, same denominator, so these add up to 1. So another interesting equation related to the angles that a vector in space forms between the 3 axes. So a couple of quick notes. When we consider these angles alpha, beta, and gamma are going to be bounded between 0 and, if we use degrees, 0 and 180 degrees. So alpha is between 0 and 180 degrees. So if we go back up here, we can see alpha is drawn here in terms of the x-axis. If our vector extended beyond 180 degrees, so if our vector was down here, for example, then instead of taking this angle, which is larger than 180 degrees, we would go ahead and look at the angle in this direction. So below, quote, quote, below the positive x-axis in this case. So alpha is always going to be less than 180 degrees. We'll just go whichever direction is closest to the positive x-axis. Finally, we can write out, so these angles and magnitude, we can write out vectors and describe them in terms of their angles and magnitude. So up here we have our vector written in terms of components. To write our vector with angles and magnitude, we can, So up here we have our vector written in terms of components. To write our vector in terms of angles and magnitudes, first we have our magnitude of v, and then we multiply that by cosine alpha I, plus cosine beta j plus cosine gamma k. So this is how we would write out our vector if we were describing it with the magnitude and the angles.